Okay, so today's class will be short one. Okay, we were discussing about the relation between the twist and the torque. So the phi is equal to the angular twist phi is equal to applied torque T into length by Gj. So Gj by L you can treat it as a like a stiffness parameter. So it relates the torque with the theta value. So T is equal to K times theta. And it's just like that P is equal to K delta, where K is equal to EA by L. So in this torsion problems, we have GJ by L. Okay, so one more thing we'll discuss about. There is one term called power used in shaft design. So the power transmitted by the shaft, it is specified and it is given in terms of kilowatt or watt or joule per second or Newton meter per second. So if you remember, there is this expression between work done per unit time that is given as force times velocity. So for shaft problems, we have this power and we can relate the power with force times velocity. Here velocity, instead of velocity, we have the angular rotation velocity of the shaft. So that is omega, and we have that radian per second. And instead of force, we have the torque. Okay, so we write the power in the torque as P is equal to, that is work done by the shaft per unit time, is given as P is equal to T times omega. So here T is the torque and omega is the angular velocity. So you can write angular velocity in terms of the frequency of rotation of the shaft. That means F means the frequency of rotation is denoted by F, and it represents the number of revolutions per second of the shaft. Okay, so W omega is equal to 2 pi F. So you can you can write angular velocity in terms of frequency, and so then the power will be written as P is equal to 2 pi F times T. T is the torque. It's not the time period. It is the torque applied on the bar. So from this we can get the torque as P by 2 pi F. Okay. And in the design problems, you are usually given the power transmitted by the torque, the angular velocity, and the allowable stress on the torque on the shaft. So you have to find what is the what should be the dimensions or what material you should use. So for that you have to find out the shear stress which is coming on the shaft. So the maximum shear stress will occur on the outer part of the shaft. So that is given as TR by J, and that should be less than tau allowable. You can find out T from this relation. P is equal to 2 pi F T. So you can T is equal to P by 2 pi F. So from that you can calculate the T value, and then you find out TR by J should be less than tau allowable. So we get T by tau allowable as J by, it should be less than minimum value of T by tau, minimum value of J by R as T by tau allowable. Okay. So J is the polar moment of inertia and R is the outer radius of the circular shaft. So this is the minimum value which we need to provide so that the shear stress will not exceed tau allowable at any point in the circular cross section. So you can pi J is pi r power 4 by 2. So J by R is pi r cube by 2. So pi r cube by 2 should be less than should exceed this value T by tau allowable. So we will solve a very simple example. We have a shaft of made of steel. It is a cross section is a tube, and the outer diameter is 50 millimeters, and it transmits a power of 100 kilowatt, and when it is rotating with a frequency of 20 hertz. So what is asked? What should be the tube thickness that should be used if shearing stress is not to exceed 60 megapascal? So tau allowable is given. Tau allowable is 60 megapascal. You are asked to find what should be the tube thickness so that the shear stress doesn't exceed this value. So what we do? So yeah, we have the radius, outer radius R2 is half the diameter of the outer diameter, so we have 25 millimeters. Thickness we can express in terms of the inner radii and the outer radii. So outer radii is R2, inner radii is R1. So T is equal to R2 minus R1. So that is the thickness. And polar moment of inertia we can write as pi by 2 R2 power 4 minus R1 power 4. So we can calculate the tau maximum, that is the maximum shear stress, which will occur in the outer circumference, that is TR by J. So T outer diameter is R2, so TR2 by J. It should be less than the tau allowable stress. So we have to find out what is the T. So we have the P value, that is the power, and that is T times omega. Omega is 2 pi f. So T value, P is given as 100 kilowatt. So 100 into 10 power 3 watt. So 1 watt is 1 joule per second, or 1 joule you can write as 1 Newton meter per second, and Hertz is 1 per second inverse. So what happens is here Newton meter per second, and here Hertz 1 by second. So second and second will cancel out, and we are left with Newton meter. So Newton meter is the unit for the torque. So T value you can get as you divide this entire expression by 2 pi 20 Hertz, you get 795.8 Newton meter. Or you can write 795.8 into 10 power 3 Newton millimeter. So that is the torque. And once we know the torque, we can apply this in this expression and find what should be the unknown R1. Yeah, so we'll do that. So tau allowable should be greater than TR2 by J. TR2 by J is the maximum shear stress occurring on the is the maximum shear stress occurring in the circular section, and it occurs on the outer circumference. So T value we got as 795.8 into 10 power 3 Newton millimeter. R2 is 25 millimeters. J value pi by 2 R2 power 4 minus R1 power 4. So R2 is 25 power 4 minus R1 power 4. And here on the left hand side we have 60 Newton per millimeter square. So if you can cancel out the units, Newton will cancel out, and millimeter square it will go there, it will become millimeter power 4. And we can send 25 minus R1 power 4 to the right hand side, and 60 to the left hand side, and 60 to the right hand side. So we get some expression. We have to find what is R1 power 4. So we can calculate, we can send R1 power 4 to the right hand side, and the limiting value for R1 is coming as 20.58. So the R1 value should not exceed, the inner diameter value should not exceed 20.58. So what we do, we write, send that R1 to the left hand side and 20.58 to the right hand side. So minus R1 should be greater than minus 20.58. R2 minus R1 should be greater than, R2 is already known, so 25 minus 20.58. So R2 minus R1 is T. So the tube thickness should be greater than 4.42 millimeter. So if the tube thickness is greater than that, then the shear stress will be less than shear the allowable shear stress. Okay, so the maximum shear stress will be less than that value. So this is a simple application of that power torque relationship formula. So yeah, there are some more things we can discuss in this torsion. Torsion of non-circular members and all, but yesterday I thought of it, but I didn't spend time on that. I spent time on something else. So another important topic is this helical spring. This helical spring topic is given in which page? So it is given in page 291, 292, 293 of Timoshenko. So again, it is not given in any other textbook. It's not there. So you have to go to the textbook and read that. So this is a helical spring. So it is it has it is made of some material, maybe like steel, and it has this circular cross section. The circular cross section diameter is d0, and it is coiling around that axis, this axis, and the radius of that circular coil shape is r, capital R. So this helical spring is taking some tensile load, or it can take compressive load also. So it is taking some tensile load, And what we are interested? We are interested in finding out what is the stress distribution in the coil. So at any given cross section of the coil, what is the stress distribution and what is the deflection of the coil? So deflection part, it is there in the Timoshenko book, but I didn't understand it, so I will not explain it. Maybe in this class I cannot explain. Maybe in next class I can try. But the shear stresses in the cross section, I understand it, so I am explaining it. So we want to find what is the stress coming on this circular cross section of the coil. One thing we'll assume is that this line, okay, this line is making very small angle with the horizontal, and we treat that this line is almost parallel to the horizontal. Okay, that thing we can assume, and we can cut a cross section, and we'll analyze the top part of the cross section of the spring. Yeah, so the forces coming on the spring are, there is this P force acting in the upward direction, and on that cross section there will be one shear force V downward, and there is a momentum on that cross section. So that moment is M, which is unknown. So this is the free body diagram, and what we can write the equilibrium equations. We can do the force balance in the vertical direction. So V will be equal to P, and we can write moment equilibrium about this centroid of this cross section. So P times R is the moment in the clockwise direction, that will be balanced by the M, which is the anti-clockwise moment. So M will be equal to P times R. So if you look carefully here, this momentum is also the twisting moment which is coming on that circular helix. Okay, so this is actually a circular helix, and there is this twisting moment. This M is the twisting moment which is coming on the tube, and we want to find what is the shear stress produced by this twisting moment M. And so the shear stress distribution will be linear. It will be 0 at the center, and it will be maximum on the outer circumference. So we can find out what is the maximum shear stress which is coming on the outer circumference due to that twisting moment M. So the formula is tau M. M represents the moment, twisting moment. So tau M max is TR by J. So here the radius of the small cross section is R, the diameter is D naught and radius is R naught. So T R naught by J naught. J naught is the polar moment of inertia of this small circular area with respect to the centroid, with respect to that x-axis, horizontal axis. So, sorry, with respect to that origin. Okay, so J naught will be pi r naught power 4 by 2, and M value, T is torsion moment will be M, and we have that radius R naught. So we get 2M by pi r naught cube. We can express in terms of diameter. So radius is diameter by 2. So 1 by 8. So 2 will go into the 8 will go to the numerator, and it will be 16M by pi d naught cube. So the shear stress distribution is 16 PR by M value is PR. So PR by 16 PR by pi d naught cube. Okay, so if you look at that circular cross section, and if you take this diameter, horizontal diameter, so the shear stress will be maximum at the ends, and it will be varying linearly. It will go to 0 at the center, and since the moment is acting in the anti-clockwise direction, so the shear stress along that diameter will be in this way. So here it will be upward direction, and here it will be in the downward direction. So this is the interior of the coil. This is the exterior part of the coil. So the interior part, it is acting in the downward direction. Exterior part, it is acting in the upward direction. So this is regarding the shear stress produced by this twisting moment M. So there is another shear stress which is produced, that is directly produced, which is the vertical shear V. It is acting on this cross section. So what we do, that vertical shear is acting in the downward direction, and the area of this cross section is pi r naught square. We assume that the tau average to be almost equal to tau max and all. For this small area, there is not much difference between tau max and tau average. So we are assuming that, and as a result, we can take the shear stress to be uniform throughout this cross section, and that is equal to the tau average. So tau average will be V by A. So V by A is pi r naught square. So it will be 4V by pi d naught square. Okay. So V is equal to P, and we have 4P by pi d naught square. So the distribution of the shear stress is uniform, and it's acting in the downward direction. The shear stress due to the shear force P. Now we have shear stress due to the torsional moment M, and shear stress due to the vertical shear V. So along the diameter Mn, we plot the shear stress. So here, due to the torsional moment, we have tau max, which is varying in this fashion, and we have on Mn we have this tau average, which is uniform. So we want to find what is the maximum shear stress. So at this point on the outer coil, tau v minus tau max is acting, and the inner coil we have tau max plus tau v. So the maximum shear stress will occur in the inner coil, inner part of the coil, this part at M, and that value is tau max, which is 16 PR by pi d naught cube, plus tau v, which is 4p by pi d naught square. So that is the maximum shear stress which is occurring in the inner part of the coil. So we can simplify this term. What we can take 16 PR by pi d naught cube common. So this term will be 1, and here we divide by here we multiply by pi by 16 r by d naught cube by r. So we will get d naught by 4r. 16 PR by pi d naught cube into 1 plus d naught by 4r. So that is the maximum shear stress, and it's occurring on the inner side of this coil at point M. So here this term d naught by 4r represents the shear stress due to the vertical shear V, and if the radius of that coil is if this radius is very high, then the effect of that shear will be less. I think that is what we have. If R is very large, then the effect of the shearing force will be less, and more predominantly the shear force will be coming from the torsional moment, torsion M, which is again equal to PR. Okay, so where do you see this heavy helical springs? If you notice, I think the railway carriages, they rest on these helical springs. Okay, I think you might, if you have seen the engines and all, there you can find these helical springs, and so this is a practical application. Know the shear stress and all on those acting on those springs. So I think it will be a compressive force, I think, or both compression and tension might happen because there is a vibration. Maybe both forces act in the force direction will change with time. So for those springs, what will happen is the inner side will have those higher shear stresses, and they are more likely to fail compared to the outer side, and usually cracking will happen here, and then it will propagate. And so this is one of the reason that the cracks happen here, because the shear stress is higher here. There is another reason that the shear stress is high. It involves little in-depth analysis. So that analysis I'm showing, it is written in the textbook, and I'm trying to explain here. So we have this portion segment of the coil. Okay, so actually this is part of the circle of radius r. So we are looking at that small arc of that circle of the circular helix. So we have one cross section AC and another cross section BF. So we assume that AC is along the diameter, horizontal diameter, and BF is also along the horizontal diameter. Now there is this twisting moment which is coming, and as a result of the twisting moment, this portion, the BF portion, will rotate by a small amount compared to this portion. Okay, there will be a small angular twist happening here. So we can find out what is that angular twist. So that angular twist is phi, and phi is equal to TL. L is the length, by Gj. J is the polar moment of inertia of the circular cross section. G is the shear modulus. So twisting moment T is of angle of twist phi is TL by Gj. Okay, so that we can calculate. And L is this AB. So that is yeah. So one thing before doing that, we'll just look at this figure in a different way. So this is the length, and twist is and this is the horizontal line, which is deformed shape, and due to the twisting moment, it will make it will deform. This point will move along the arc and reaches this point, and this angle subtended to the center is phi. The radius of this cross section is r0, and there will be this shear. If you can join this point with this line, and we'll get the deformed line, and that line makes an angle. That angle is gamma shear. Okay, so we have L times gamma, that will be the length of this arc, and that will be equal to R0 times phi. Okay, so R0 times phi is same for this cross section and this cross section, but what will happen here is the length will be different. Gamma shear, as a result, gamma shear will be different. So let's write that equation. So for this, if you draw a line here, let's say line, and after deformation there will be this gamma shear. Okay, so there will be some gamma shear occurring here. So let's denote that as gamma AB. So the length is AB. So let's write LAB. Okay, so this gamma shear strain for this line, gamma AB times length AB is equal to R0 times phi. R0 times phi is the angle of twist. Yes, we are using simple relation. L times gamma shear is R0 phi. So for AB, the shear is gamma AB and length is LAB. So gamma L for AB is R0 times phi. Similarly, for this line, there will be some shearing strain, and that can be expressed as gamma CF LCF. Okay, so that gamma CF LCF will be equal to again R0 phi. But here the main point is that this part, this entire segment is part of an arc of a circle of radius capital R. So this is closer to the center. AB is closer to the center compared to CF. So the length of AB will be less than the length of CF. So arc length AB will be less than arc length CF. That means length of AB, LAB, is less than length of CF. So in that scenario, what will happen to the shear strain? Gamma AB is R0 phi by LAB. So since LAB is, and gamma CF will be R0 phi by LCF. So LAB is less than LCF. So R0 phi by LAB will be greater than R0 phi by LCF. That means the shear strain gamma AB is greater than shear strain gamma CF. Okay, so shear strain coming here. That means at AB there will be a larger movement of the point B along the arc. So B prime will be, I think no, gamma shear will be more. B prime will be FF prime, but the angle gamma shear which the AB makes A prime AB prime makes with AB will be higher. Okay, so gamma AB will be greater than gamma CF. Okay, so that C prime will make CF prime will make a higher lower value that with the horizontal compared to this AB prime. Okay, so there will be highest shear strain coming on the inner side of the coil. So when there is a higher shear strain, there will be correspondingly higher shear stress. Okay, so this is another reason why the failure will usually occurs in the inner part of the coil. So they had there is some paper which the textbook refers, and we can get the actual shear stress distribution in the inner side. So the tau max value, which is 16 PR by pi d naught cube, and there is some factor coming here. Instead of 1 plus 4R by d, d naught by 4R, we have this 4m minus 1 by 4m minus 4 and 0.615 m by m. Okay, so yeah, so here m value is 2R by d. So this is some modification which is done to the shear stress to account for this this analysis. Derivation, it's not there in the textbook, but if you have to refer to the paper and see that how these terms are obtained. Okay, so this brings the today's class to a conclusion. There is one more thing which is described, which is the deflection of these coils. It is given in the textbook, but the problem is I'm not understanding it. So